Hello everyone. Today we will talk about sampling and descriptive statistic. We will learn about certain terms we will be using more often in the coming chapters. Okay, we want to know, why do we need to learn probability and statistics for engineering? The first thing is, as engineer, you always make measurement. You carry out experiment. You build system. Unfortunately, there is noise with everything you do. And because of this noise, the outcome may come different than what you expect. In this case, probability and statistic will help us to figure out what's the problem. And sometimes you take measurement of unknown mechanism and you try to reach a conclusion. You collect data and you want to reach a conclusion. These data may come from the galaxy or from human body or biological system, and you don't know how this system is operating. You are just collecting data. Then by looking at the data and do some statistical analysis, you can reach some conclusion about the mechanism that generated the data. If you carry out an experiment and you have an input, you have an output, you make a measurement, probability and statistics will help you to reach a reliable conclusion. For example, the gain of an amplifier with certain certainty. What is the gain? Is it 40 plus minus 1 or 2? And by learning probability and statistics, you will be a well-informed member in the society. And as a good example, in election, they do a survey. Then they try to predict who will win the Senate position or the president. Now, after taking this course, hopefully you will realize and you will be able to understand these terms and even to make a good judgment. Is this survey will reflect the people vote or not? Is there some flaws in this survey? Or in the stock market, why is it fluctuating? Hopefully by the end of this semester, you will know how to interpret the fluctuation in the economy or in the stock market. So that is probability and statistic, but we will look at it from engineering point of view. Let's look at this example. So imagine you have a machine that produces amplifier for medical instrumentation, and you label this amplifier, the gain is 45 plus minus 2. Now, every day you are manufacturing probably 1,000 amplifier or 1,000,000 amplifier, but there are always noise and uncertainty. When the machine gets hot, maybe it's not producing the amplifier with the specification you designed the system. So how will you know at the end of the day if the amplifier produced the 1,000 meet the specification that the gain is 45 plus minus 2? So you're going to take a simple random sample out of the 1,000, probably going to take a 50, let's say, and test them and see if the 50 meet that specification, 45 gain plus minus 2. Now the question is this 50 amplifier you selected randomly from the 1,000 is a good representation of the 1,000? For example, let's say this is the population. You have 1,000 amplifier. You take a sample of size 50. You measure the gain, and here you are assuming the average gain is 45 plus minus 2. So in this sample of 50, the average gain came maybe 48. You take another sample, definitely the average gain will be not exactly 45, not 48, maybe 43. And so forth. And maybe this sample, the gain will be 45. So how large should you make this sample to minimize this variation? So you will have a good estimate of the mean of the amplifier you designed. So that is a question you have to answer as an engineer. The second question, when you estimate, you have a population and you want to estimate mu. So there is a possibility you're going to say, okay, the average gain is 45 plus minus 2. With what certainty you are sure that is true? Maybe you're going to say it is 90% I am certain. What if I want to give me an estimate of the range with a higher certainty? Then you may say, okay, it is 45 plus minus, what do you think? if I want to be more certain, like 95%, then I will increase the range to cover all possibility. So we will learn how do we determine that range with specific certainty. Or sometimes when a company come and sell you this amplifier and they say, oh, our amplifier is 45 plus minus 2 and we are sure 90%. That's their claim. As an engineer, how do you verify this claim or hypothesis? Should I accept it or should I reject it? That's what we will be learning in this probability and statistic course. So first we have to learn some term that we will be using. So we talk with each other, we know what we are talking about. The first thing is population. What do we mean by that? That means it's a set of all possible outcomes in the experiment or measurement you are taking from a phenomena like a radiation from the sun or light intensity coming from a star, something like that, or a signal coming from the human body. So a population will contain every possible outcome that comes in a measurement or outcome of an experiment. Now, when we talk about a sample, this is a subset of the population. Then we call this a sample. That sample could be of size 5 or of size 100. Then that's what we talk about sample. A simple random sample is a sample that I take of size n, but the element in this sample, x1, x2, I pulled x1 out of this population with equal probability as if I am pulling x2, as if I am pulling x3. Then this is a simple random sample. That means I did not pull out certain outcome that I favored, but I used a mechanism to make picking this data from this population to this sample with a total randomness. So knowing what is the first data point, I will not be able to tell what is the value of the second data point. Then this is a simple random sample. And in probability statistic, when we sample a population, we always want to make it SRS. For example, here, let's say you have a university and the students or the population consists of 50,000 students. And you want to generate a sample of 100 to measure maybe the height or the GPA of the student. Now, it will be SRS, a simple random sample, if I label, for example, all students, number them from 1 to 50,000, then I generate in the computer a code that will generate a random 100 number from 1 to 50,000. Then I will pull these 100 students at random. But if I go, for example, to the athletic department and pull 100, then that will be not simple random sample, because I pulled these 100 sample from a certain department. Maybe they are basketball, so they will be all tall. Then that will not be a simple random sample. Now, when we talk about a sample of convenience, sometimes you have no choice. You just cannot make a total random sample. For example, let's say you have a machine that produces 1,000 blocks and you put the block on top of each other. At the end of the day, you want to take a sample of 10 blocks to measure the weight, to estimate if the machine is working properly. To make it SRS, that means you have to take a block from way at the bottom pile, the top, the middle, and that's too much work. So you will end up probably take 10 blocks from the top piles, and hopefully the machine will be working the same way from the morning until the afternoon. And that's what we mean by sample of convenience. Or for example, you want to do a drug test on a population. SRS sample, that means you have to cover all race and ethnicity to test your new drug on. Maybe in the city you are living in, there is certain ethnicity, there are not enough of them. So then your sample will be sample of convenience. We try to avoid sample of convenience as much as possible. Now, when we have a population and we take samples, there will be always sampling variation. So the mean of this sample, if it's 50, will be different than if I take another sample of size 50. So this means will be some variation. We always want to minimize this variation. So what do you think? Should I make the size more, larger, or simpler to minimize the difference between mu1 and mu2 and another sample here? Common sense, we should increase the size of the sample. The larger the sample is, then this variation will be smaller. And we will learn that in more detail. But that's what we mean by sampling variation. Now, we say the items in a samples are said to be independent if I take these samples and the way I chose X1 is total randomness. The way I chose X2 does not depend on what I choose in X1, and the same for X3. Does not depend on X1 and X2. Then we say these items are independent. If the size of the population here has only like 25 elements and I am taking a sample of size 5 and here is 5, then the items here X1, X2, X5 will not be independent, because if I already chose 4 out of here, what's left here is 21. So I can predict the fifth one what value it will come out because I already took 4 out. So in general, we can claim the items here are independent if the size very small. The size of the sample is 5% or less of the population. Then we can claim, yes, the items in the samples will be independent. And that's the rule of thumb. Okay, now type of data. We have 2 types of data. The first one is numerical, and sometimes we call it quantitative. And the second type of data is categorical or qualitative, we call it. Numerical is when you can assign a number to the data point in the population. For example, height, that's numerical. Voltage, numerical. Light intensity, numerical, or quantitative data. Categorical or qualitative data, when you can describe it, you cannot assign number, but it follows a certain category, like color, for example, red, yellow, a zip code, ethnicity, country of origin. Then these we call them categorical or qualitative. Or, for example, correct or wrong, that is also categorical. The second thing is controlled experiment. That's another item we will be using. What do we mean by controlled experiment? Controlled experiment, that means I am the experimenter. I can control what's the input and then measure the output. I design the system and I'm testing this system. I apply certain input, then I observe what's the output and reach a conclusion. Then this we call it cause and effect. Cause, that means I control the input. The effect I study on the output. That's his controlled experiment. But there are different experiments that I have no control over it. And this we call it observational study. Like we are observing the galaxy. I cannot control the motion of the sun or the reaction inside the sun. All I am doing is observing the radiation and try to reach a conclusion about the mechanism inside the sun. Or sometimes I observe the blood pressure in the body. I cannot control it. I don't want to control it, but I want to see the health of the person. So I observe certain output from the human body. It could be ECG, it could be blood pressure or glucose in the blood and so forth. Then we call this observational study. So we have controlled experiment and observational study. The next section is summary statistic. And this is a simple calculation that gives us a good idea about a population or about a sample. So if I have a population and I take a sample of N10 and I need to find the sample mean. So let's say here is X1 all the way to X10. If I need to find the sample mean, then I just add X1 plus X2 plus all the way to X10 and divide by the size of the sample N. And that's what this one. Now, I need to calculate the sample variance. That's mean the data point here, how do they vary from each other? Usually as engineer, when we design a system, we want the variance to be as small as possible. That means our system we designed is perfect, always give us the expected output. To calculate the variance, what we do is, first we calculate the mean. Then we find the difference between each element in the sample with the mean, and we square it. Then plus the difference of the second element from the mean, and we square it. Why do we square it? Because if you don't square it, this difference sometimes will become positive, sometimes the difference negative, and you add them up, you end up with 0. Does that mean there is no variation? No, there is variation. So that's why we square it to make sure it's positive. And plus xn minus x squared. And after you add all the differences, then you average it by 1 over n minus 1. And mathematically, it's expressed as here. It's a summation of the difference squared and divided by n minus 1. Make sure it's n minus 1. Some statistical software, they divide by n. If the size is very large, then n or n minus 1 will not make a difference. But if the size is small, n minus 1 is a better representation of the variance. Now, if I take the square root of s squared of the variance, then that will be the sample standard deviation. So s then is just the square root of s squared, the sample standard deviation. So s squared is the variance, s is the standard deviation. If I need to calculate the variance, I can use this equation, or it's more efficient to use these equations. And they are the same, they will give you the same value. But here, using this one faster, even when you write a code. Why? Here, see, you are using n subtraction and n squaring. In this case, no. You are just using n squaring and 1 subtraction. So that is much faster even in a quiz and the test to use these equations. And if you want to show the proof, this is the same as this one. What we can do, we can start with this. So we can say s squared equal 1 over n minus 1 summation. Square this one. So that will be xi squared minus 2xi x bar minus x bar squared. And this is 1 over n minus 1 summation xi squared minus, I will put the summation multiply by each one of them, minus 1 over n minus 1 2xi x. So this is 1 over n minus 1. Now, this one here, x bar and 2 has nothing to do with the summation, so it can come out, and this will be xi. Now, here, this one, I am summing x bar. X bar is a constant, so I am summing it n time. I goes from 1 to n. So this is just n x bar squared. And don't forget the n minus 1. I can take the 1 over n minus 1 out here, and this will be xi squared minus 2x bar. I can multiply this by n and divide by n xi. N x bar squared. Now this quantity here is just an average. So this is 1 over n minus 1 xi squared minus 2x bar and x bar n x bar squared. And this is 1 over n minus 1. Now here you have minus 2 n x bar squared, and here n x squared. So that is will be minus n x bar squared. And that's exactly the same as this one. And it's easier to calculate using this one. Now, what if you have another variable or another sample that depend on a different sample, but with certain equation. It could be amplification, adding a DC voltage. So let's assume you have a sample Y that depend on another sample Xi. Later on we will call them variable, amplified by B, and there is a DC voltage added to it, or a constant. Or you can think of this is a Fahrenheit temperature that you are measuring, and this is centigrade. Now I need to find the mean of Y. So to find the mean of Y, it will be the mean of A. A is a constant, so the mean of a constant is just a constant, plus B is a constant, multiplied by this sample. The mean of this sample is X. So the mean of Y will be A, the constant, plus B, the amplification, and the mean of X. How about the variance? The variance of Y. If I want to find the variance of Y, it's the variance of A plus the variance of B, Xi. Now this variance of Y. Now what is the variance of a constant? A constant is a constant, never change value. It's fixed, so there is no variation. So the variance of a constant is a zero, so that's a zero. But what is the variance of X multiplied by B? Just to see it conceptually, will this variance increase or decrease? Intuitively, it will increase. If X, for example, if X here, this is the variation. I have a sample is equal 2, another sample equal 3, another sample equal 4, another sample equal 1. So there is some variation. Now, if I have Y equal 2X, that means that will be 4, that will be 6, that will be 8, that will be 2. Now there is more variation between 4, 6, 8, 2 in comparison to this. So we know the variation or the variance will be larger, but by how much? Well, what we can do is we can carry out the variance is 1 over n minus 1, the sample, which is in this case bxi, minus the mean of xi, and we just found the mean bx squared. And this will be 1 over n minus 1 summation. If I square this one, it will be b square xi square minus 2b square xi x bar plus b square x bar square. And if I take b square, that will be b square over n minus 1 summation of xi square minus 2 xix plus x bar square. And this is b square 1 over n minus 1 summation of xi square minus 2xix. Now I can rewrite this. I can rewrite this as xi minus x squared. And this here is the variance of x. So that's b squared, the variance of x. And that's the relationship. So if you have two samples related by this equation, the mean of y is a plus b, the mean of x. The variance of y is the variance of x multiplied by b squared. We just show it here, and this relationship you will see it more often. So make sure you understand the proof and you know how to use it. The next one is outlier, and that's very important. When you run an experiment and you collect the data and you found one data point, the value is just either extremely low or extremely high. Now that data point is an outlier. And does that mean you discarded? It could be an outlier because you made a mistake in the measurement, or when you wrote the data point, you made a mistake in writing it. So that could be an outlier and you just easily remove it. But you have to be very careful. It could be a true data point and it's extremely high because there is a reason for it and you are not aware of it. So you have to go back and investigate. and run the experiment again or make the measurement again to make sure you see that data point again. And if you see it, that means there is a mechanism that generates this extreme case. And you investigate it and you study and you find the reason. Like, I remember in one of the experiments, I was measuring the hearing on a patient. So I was playing a tone of different frequency. So as I go with frequency, usually for a typical human being, we are more sensitive to the tone of 2000 hertz, less sensitive to low, less sensitive our hearing to high frequency, high tone. But when I was testing a cochlear implant subject, I noticed there was like a region of frequency, suddenly it just went down. And I thought at the beginning I made a mistake in the measurement. But then I called the participant and I asked him if I can run the experiment again, and we run the test again, and I kept getting this low. Then when I investigated and I read publication, there is in the cochlea, we have all this auditory nerve. This is sensitive to high frequency nerve, this is sensitive to low frequency, and this is middle frequency. That range of frequency, the subject was not able to hear because it was damaged, the auditory nerve in that region that correspond to this frequency. And that's why he wasn't able to hear. I could have said it's an outlier, I made a mistake, and assume it looks like this, but no, we cannot do that. We have to investigate it. So that's the outliers. And when you run research and experiment, you will always get this possibility. Now we know how to calculate the mean. Now the median, if you have a population of different, or sample of different value, and I want to find the median. The first step, make sure you do that. The first step, organize this data point from lowest value to highest value. For example, the lowest value could be 1, the highest value is 100. So I order them from lowest to highest. Then I look at the data point that is in the middle. So 50% of the data point has a lower values than the median, and 50% of the data point have values larger than the median. Then that is the median. And how do we find it? We first, after we arrange them from lowest to highest, then the position of the median will be 0.5 times n plus 1, where n is the number of sample. So in this case, let's say I have 100 data point, then 0.5 times 100 plus 1, that is 50.5. So the median in this case, 50.5, that's a position. There is no position 50.5. It's either 50, 51 position, 53 position is integer. So when I get this scenario, then the value of the median will be the average of 50 and 51. And that will be the value of the median. In this case, mean all first 50 data point will be lower than the value. The next 50 data point will have larger values than the median. But let's say then the size of the sample or the population is odd, like 101. So then the median will be 0.5 times 101 plus 1, that's 51. So the median will be the value of the data point at this location. That will be the median. So that's how we find the median. Now quartile is, if I want to find the value of a data point such that 25% of the samples are less than this value and 75 more. So I have a sample and I have all these data, and they need to find the first quartile, the value of the data point here, such that 25% of the data will have values less than this and 75 more. And we call this the first quartile. And how do we find it? Again, the same thing, 0.25 times n plus 1. And same thing, if you get an integer, then the value of the data point located in this integer will be the first quartile. If you get a fraction, then in this case you find the average of the lower data point. For example, if I get here 5.7, then the data point at the location of 5 and at the location of 6, I average them, and that will give me the first quartile. Just make sure when you do this, you arrange your data first from lowest to highest value. Now, if we want to find the third quartile, then it is 0.75 times n plus 1. That will give us the third quartile. If I want to find percentile, that means I don't want to find the 75th percentile, which is the third quartile, but maybe I want to find the 60th percentile. So how do I find it? Same equation here. 60th percentile, 0.6 or 60 divided by 100 times n plus 1. The first quartile is 0.25. The third quartile is 0.75. Any percentile, just use the same equation. This is just a summary of first quartile is the 25th percentile, the median is the 50th percentile, and the third quartile is the 75th percentile. Let's see this example. Suppose we have the following data. Here they already sorted them for us. But imagine if I gave you the original data is 2, 11, 3, 7, 5, 6, 9, 15, 25, 9. And I ask you to find the mean, the median, the first quartile. The mean, it's okay. So let's call the random variable or the sample here x. So the mean will be 2 plus 3 plus 5 plus all the way 25 divided by 10. Now the median, we have to be careful. So we have to sort these data points from lowest to largest, which will come these. And then the median will be 0.5 times n plus 1. In this case, that will be 0.5. N is 10, so that's 10 plus 1, 11. So that's 5.5. So I look at the fifth and the sixth, and I average them. This is the first, second, third, fourth, fifth, and the sixth. So the median, let's call it mx, is the average of 7 plus 9 divided by 2. So that's 8. So my median is 8. That means half of the data will be less than 8 and half of the data more than 8. So this is the first half, 1, 2, 3, 4, 5 data point, and half of them larger than 8. What's the first quartile? It's 0.25 times n plus 1, so that is 0.25 times 11. That's 11 divided by 4, 2.75. So I average the second and third data point. So 3 plus 5 divided by 2, that's 4. So the first quartile, I can say x 0.25 equal 4. And you can do the same thing for the third quartile. That will be 0.75 times 11. And that will give you the position. And the position here, you get 8.25. So you average 8 and 9. 8 and 9, that's the 8 and that's the 9. So that will be 11 plus 15 divided by 2. And that will be 13. Now, when we have a data, sometimes we want to do statistical summary. In this case, numerical data. The numerical summaries, we have two things. One, we call it frequencies, and the other one is sample proportion or relative frequencies. So you have the population here. It could be this population, the GPA of the students. Now I can say 3.3. Here, maybe my population is 1,000 students. I can say 3.3 happened 221 times. That's frequency. 3.0 maybe happened for 400 students. That's frequency. Now, when we say sample proportion or relative frequency, now we talk about percentage. So now I can say 3.3 happened 222 divided by 1,000. Now that's a percentage or relative frequency, and this is 0.221. So that is a probability or relative frequency. So it is like 22.1% of the population have 3.3 GPA. Make sure you understand the difference between frequencies. It's the number of time it happened. Relative frequency, you list a percentage, probability. If we take this example, 100 rivets are checked for their braking strength. If 4 of the rivets fail, find the sample proportion of rivets that fail. If I want to specify, the frequencies is 4, but the relative frequency will be 4 divided by 100, so that is 4% or 0.04. That's the relative frequency. Okay, the last topic in this lecture is 2 terms we will be using more often: statistics and parameter. And these relate to a population and a sample. So this is the population and this is a sample. And the population may have X1, X2, 1,000 data point. And the sample may be of size n equal 20. If I find the mean of the sample, or the variance, or the standard deviation, or the probability related to data in the sample, then we call it statistics. And we will use this term more often in coming chapter. Make sure you understand that. If I find the mean of the population, or the variance, or the standard deviation, or probability, then we call these parameter. So a numerical summary of the population data points is parameter. A numerical summary of the data points in a sample is statistics. So we always trying to estimate the mean, the variance, the probability of a population by using a sample, and that's why we call it statistic. It's an estimation or trying to figure out the parameter of the population. All right, thank you. And next video we will finish this chapter and talk about graphical summaries and so forth and plots.